Welcome to Lecture 5 of Information Theory course on ISSS. I am your instructor Sachin from the Indian Institute of Science. Just a quick recap before the lecture. So, in the previous classes, we studied what are convex functions. Convex function f is a function such that f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2, where lambda is some number between 0 and 1. Using that, we proved Jensen's inequality, which says that the expected value of the function of a random variable is greater than or equal to the function of the expected value of a random variable when the function is convex. And when it is strictly convex, this equality holds if and only if x is a constant and x is equal to expected value of x. Then we saw the information inequality, which says that relative entropy between two probability mass functions p and q is greater than or equal to 0 with equality if and only if the two probability distributions are equal for all values of x in the alphabet. Then we saw that non-negativity of mutual information. So since mutual information between two random variables x and y is the relative entropy between the probability distributions p of x, y, which is the joint probability distribution, and the product of the marginal distributions p of x, p of y, um, from the information inequality, the mutual information is also greater than or equal to 0, with equality if and only if the two random variables x and y are mutually independent. Then we saw that the conditional relative entropy d of p of y given z parallel q of y given z is also greater than or equal to 0, with equality if and only if p of y given z is equal to q of y given z, only for values z such that p of z is greater than 0. Then we saw that this non-negativity holds for conditional, even when you condition mutual information. That is, I of x semicolon y conditional on z is greater than or equal to 0, and equality holds if and only if x and y are conditionally independent given z. And finally, we saw that the entropy of a random variable x is always less than or equal to log of the cardinality of the alphabet script x, that is the number of outcomes that a capital X can take, and the entropy of the random variable x is equal to the log of cardinality of script x if and only if x has the uniform distribution of script x. So these are the things we studied in the previous classes. This class will start out with a theorem. Give me 2 minutes. I'll be right back. I'm back. So we'll start today's lecture with the following theorem. Conditioning reduces entropy. In other words, information can't hide. Precisely, h of x given y is less than or equal to h of x with equality if and only if x and y are independent. That is, by if there are two random variables x and y, where y might contain some information about x, knowledge of y cannot increase the uncertainty in x. So it might decrease or it might not change anything about the uncertainty of x. A proof is simply one line. We know that mutual information is non-negative, but mutual information is also equal to I of x semicolon y is also equal to h of x minus h of x given y. So h of x is greater or equal to h of x given y by moving h of x given y to the right side of to the left side of the inequality. Here, when we say that h of x is greater or equal to h of x given y, it is only on average. That is, by knowing a particular value of y, we might increase or decrease the uncertainty in x. But on average, we will always decrease the uncertainty in x. And that can be shown through an example. So let two random variables x and y have the following joint distribution. Then h of x is h of this distribution. So the distribution of x is probability of x is equal to 1 is 0 plus 1 over 8, which is 1 over 8. Probability that x is equal to 2 is 3 over 4 plus 1 over 8, which is 7 over 8. So uncertainty in x is h of 1 over 8 comma 7 over 8, which turns out to be 0.544 bits. You can do the calculation yourself and verify. Now h of x given y is equal to 1 is h of this distribution. So you have to normalize that distribution. When you normalize it, you will get h of 0 comma 1, which is nothing but 0 bits. That is, since if you know that y is equal to 1, then x takes the value 1 with probability 0, and x takes the value 2 with probability 1. So there is no uncertainty in the value of x because you can never take the value 1. That's why the entropy in x given y is equal to 1 is 0 bits. Similarly, h of x given y is equal to 2 is given y is equal to 2, x has that distribution. So we have to normalize that. We normalized it by dividing it by 1 over 4, which is the sum of uh, all the entries. 1 over 8 plus 1 over 8 is 1 over 4. So it's the distribution is the entropy of the distribution half comma half, which is nothing but 1 bit. Then if you find h of x given y on average, so it's probability that y equals 1 into h of x given y equals 1 plus probability that y equals 2, h of x given y equals 2. Probability of that y is equal to 1 is the sum of these two, which is 3 over 4. This becomes 3 over 4 times h of x given y equals 1 is 0 bits, plus probability that y is equal to 2 is 1 minus 3 over 4, which is 1 over 4, times h of x given y equals 2 is 1 bit. So uncertainty in x given y is 1 bit. So from this you can see by knowing that y is equal to 2, the uncertainty in x increased to 1 from 0.544. But if we know that y is equal to 1, then the uncertainty in x is 0, which decreased the uncertainty in x. So individual outcomes might increase or decrease the uncertainty in x, but on average, h of x given y is 1. Sorry, it's not 1 bit. This is 1 over 4, which is 0.25 bits, which is less than h of x, 0.544 bits. So on average, knowing the value of y will reduce the uncertainty in x. That is an illustration of the theorem that I proved earlier. That is conditioning reduces entropy. Using this, we can derive another theorem, which is called the independence bound on entropy, which says that let x1, x2 up to etc. up to xn be random variables drawn according to a probability distribution p of x1, x2, etc. up to xn. Then h of x1, x2, the joint entropy is less than or equal to sum of individual entropies with equality if and only if xi are independent. So here also the equality if x and y are independent, that comes from the equality of mutual information to 0 if and only if x and y are independent. So the same condition will hold for h of x equal to h of x given y. The proof of this independence bound is as follows. We use the chain rule and we can write h of x1, x2 up to xn is summation h of xi given xi minus 1 to x1, which is less than or equal to summation h of xi I is equal to 1 to n, because for each of the values of I, h of xi given x1 to xi minus 1 is less than or equal to h of xi, because conditioning reduces entropy. And equality holds if and only if the equality holds for all I. That is, xi is independent of x1 to xi minus 1 for all I. Therefore, all xi's are independent. Now we come to an inequality which we call the log sum inequality. Let- We'll take it as a theorem which says for non-negative numbers a1, a2 up to an and b1, b2 up to bn, the summation of ai log ai over bi summed over all I is greater than or equal to summation of ai is equal to 1 to n times log of summation of ai is equal to 1 to n divided by summation of bi is equal to 1 to n. With equality if and only if ai over bi is a constant. We follow the general convention 0 log 0 is equal to 0, 0 log a over 0 is infinity if a is a positive number, 0 log 0 over 0 is 0. With that convention, we can assume without loss of generality, I'll write that as WLOG, without loss of generality, that AI and BI are all positive. For the cases where AI, BI are zero, if AI is zero, then the term will uh, be zero here, it will be zero here, and it will be zero here. So it won't affect the summation. If BI is zero and AI is zero, then again it won't affect the summation. If for some AI is greater than zero, but BI is zero, then this side will be infinity, and you'll get infinity greater than or equal to some finite quantity, which is again fine, which the inequality will hold. So we only need to check when AI is greater than 0 and BI is greater than 0. For that, observe first that f of t is equal to t log t is a strictly convex function for t greater than 0, because f dash of t is t ddt of log t plus log t ddt of t, which is t into 1 over t plus log t into 1, which is 1 plus log t, and f double prime of t is 0 plus 1 over t, which is 1 over t. F double prime of t is greater than 0 if t greater than 0. With that, uh, we had a previous theorem which we proved that said if the second derivative is greater than 0, then for a function in some interval, then the function is convex in that interval. It's strictly convex if it is greater than 0, convex if it is greater than or equal to 0. Now for this function t log t, we can apply Jensen's inequality. So by Jensen's inequality, summation of alpha I f of ti greater than or equal to f of summation of alpha I ti for all values alpha such that alpha are positive, summation of alpha I is 1. So if alpha I greater than or equal to 0 and summation is 1, then that could be a probability distribution for the values of ti. Then this side is actually the expected value of f of ti, and this is the f of expected value of ti. Now we can set alpha a is equal to bi over summation of bj, j is equal to 1 to n, and ti is equal to ai over bi. If we substitute this and the meaning of the function f, which is t log t, we'll get summation of summation over all I. Alpha I is bi over summation over all j bj times t log t, where t is ai over bi, log of ai over bi. This is greater than or equal to summation bi over summation bj, which is alpha I times ti, which is ai over bi, into log of summation bi over summation bj times ai over bi. This bi will cancel in all these terms, and the summation bj here and here will, they are constants, so they can come out of the summation. You can take them out of the summation and cancel them, and you will be left with summation over all I ai times log of ai over bi is greater than or equal to summation over all I of ai times log. So summation over all I ai over summation bj. Summation bj is a constant. We can take that out. You will get summation ai over all I divided by summation bj over all j, which is the log sum inequality. Next, we have a result that we had proved earlier, the information inequality d of p parallel q greater than or equal to 0 with equality if and only if p is equal to q. Okay, we didn't discuss the equality condition here. So for a strictly convex function, the equality condition holds if the probability, sorry, if x is a constant value with the probability x is equal to expected value of x with probability 1, that is x takes a constant value. So here x is ai over bi, so ai over bi must take a constant value. That's the equality condition. Okay, next we use this log sum inequality to prove the non-negativity of relative entropy. Relative entropy we can write for pmf p and q as summation over all x in script x p of x log of p of x over q of x, and this becomes from the log sum inequality summation over all x p of x times log of summation over all x P of x divided by summation over all x Q of x. We know that summation over all x P of x is 1 and summation over all x Q of x is also 1. So this is 1 times log of 1 over 1, which is 1 times log 1, which is 0. With equality, if and only if P of x over Q of x is equal to a constant, but summation P of x will be equal to constant times summation of Q of x, which implies the constant is equal to 1 for all x. Therefore, d of P parallel Q is greater than or equal to 0 with equality if and only if P of x equals Q of x for all x. Next, we'll see some consequences of the logsum inequality. We'll start with the following theorem. Convexity of relative entropy. It says that the relative entropy d of P parallel Q is convex in the pair PQ. More precisely, if P1, Q1 and P2, Q2 are two pairs of probability mass functions, then d of lambda P1 plus 1 minus lambda P2 parallel lambda Q1 plus 1 minus lambda Q2 is equal to lambda times d of P1 parallel Q1 plus 1 minus lambda times d of P2 parallel Q2 for all values lambda belonging to 0, 1. The proof is as follows. Taking A1 is equal to lambda P1 of x. A2 is equal to 1 minus lambda P2 of x. So before that, we have to first convince yourself that lambda P1 plus 1 minus lambda P2 itself is a probability distribution. So since lambda is a non-negative quantity, P1 and P2 are non-negative. 1 minus lambda is also non-negative. Their sum is convex combination is non-negative. And the summation of lambda P1 of x plus 1 minus lambda P2 of x is the summation of lambda P1 of x plus summation of 1 minus lambda P2 of x, which is lambda times the summation of P1 of x plus 1 minus lambda times summation of P2 of x. Summation is over all x in script x, which in turn is equal to lambda plus 1 minus lambda, which is 1. So uh, lambda p1 of x plus 1 minus lambda p2 of x is indeed a probability distribution for the random variable capital X if p1 and p2 are probability distributions. Similarly, q1 and q2 are probability distributions on random variable x. So lambda q1 plus 1 minus lambda q2 is also a probability distribution. So it makes sense to take the relative entropy between lambda p1 plus 1 minus lambda p2 and lambda q1 plus 1 minus lambda q2. Given that, by taking a1 as lambda p1 of x, a2 is 1 minus lambda p2 of x, b1 is lambda q1 of x, b2 is 1 minus lambda q2 of x. Using log sum inequality, you can then say summation I is equal to 1 to 2 ai log ai over bi is greater than or equal to summation ai times log of summation ai over summation bi. So that is a1 log of a1 over b1 plus a2 log of a2 over b2, which is a1 is lambda p1 of x log of lambda p1 of x by lambda q1 of x, that's b1, plus a2, which is 1 minus lambda p2 of x log a2 over b2, which is 1 minus lambda p2 of x over 1 minus lambda q2 of x. This is greater than or equal to summation of ai, which is a1 plus a2, which is lambda p1 of x plus 1 minus lambda p2 of x, times the log of summation of ai divided by, so here you can cancel out these lambdas, here you can cancel out 1 minus lambda, and you will be left with lambda times d of p1 parallel q1 plus 1 minus lambda times d of p2 parallel q2 is greater than or equal to d of lambda p1. Okay, so this is one for one particular value of x. You have to take the sum over all x in script x on both sides. I'll get summation over all x p1 of x log of p1 of x over q1 of x, which is d of p1 parallel q1, and so on for the other terms. So we'll end up with d of lambda p1 plus 1 minus lambda p2 parallel lambda q1 plus 1 minus lambda q2. And that's the proof. So we have shown that the relative entropy is a convex function, and using that you can write out a theorem about entropy itself. Concavity of entropy says the entropy h of p is a concave function of p. Proof is there are two proofs. I'll give you the simpler proof. H of p is log mod script x minus d of p parallel u, where u denotes the uniform distribution on mod script x outcomes. Since d is convex, which we saw just 2 minutes ago, h is concave because if d is convex, so minus d is concave. So this part is a concave function. This is a constant function. So you add a constant function, you don't change the concavity or convexity. That's why minus d log mod x minus d of p parallel u is concave. It follows directly from the convexity of d. So what exactly does that mean? It means that if P1 and P2 are two probability mass functions on the same alphabet, then for any lambda value between 0 and 1, lambda P1 plus 1 minus lambda P2, as I told you earlier, is also a PMF in the same alphabet script X. Then concavity means the entropy of the distribution lambda P1 plus 1 minus lambda P2 is greater than or equal to lambda times the entropy of the distribution P1 plus 1 minus lambda times the entropy of the distribution P2. In words, you can say if we mix two distributions with equal entropy, the entropy of the mixture cannot reduce. So by mixing two distributions, what we mean is, suppose suppose you're doing an experiment. Uh, Say you're rolling a die and seeing what the number on the face of the die is. So you have two different dice. One has A uniform probability, that is, each of the phases 1, 2, 3, 4, 5, 6 is equally likely to occur, and another has different probability. All the outcomes are not equally likely. Then you have a coin, so you toss the coin, and if the coin turns up heads, you use the first die, which gives you outcomes with equal probability. And if you toss the coin turns up tail, then you use the second die. You roll the second die and note down the outcome. So now the coin itself has some probability of falling heads and tails. So that is given by lambda and 1 minus lambda. So the probability that the outcome of the dice is roll of a die is 1 is uh, lambda times the so it's probability that you get a heads, which is lambda, times the probability that you get a 1 when you roll the die associated with heads, which is P1, plus the probability that you get a tail, which is 1 minus lambda, times the probability that you get a 1 when you roll the die associated with the tail, which is P2. So you're mixing two different distributions, and when you mix two distributions with equal entropy, then the resulting distribution will have at least the same entropy. You cannot get a mixture with lesser entropy. In thermodynamics terms, if you mix two gases with the same entropy, then you will increase the entropy of the overall mixture will have a higher entropy. Next, the concavity or convexity we have seen for relative entropy, and for entropy we'll see that now for mutual information. So for mutual information, you need two random variables distributed according to the joint distribution P of x comma y, which you can expand as P of x times P of y given x. That's basic probability. Then the mutual information I of x semicolon y is a concave function of P of x for fixed P of y given x, and a convex function of P of y given x for fixed P of x. So since P of x comma y is P of x, P of y given x, if you fix P of y given x, then that is, if you fix in terms of communication, it would be the channel transition probability. Then by varying the distribution of x, you can vary the joint distribution x comma y. So the joint distribution x comma y is now simply a function of the distribution of x. Similarly, if you fix the distribution of x, then the joint distribution of x and y is a function of the conditional distribution y given x. So by fixing, what we mean is that um, so suppose you have a die and you're tossing the die. There are six possible outcomes, and the probability mass function px of x is given by p1, p2, p3 up to p6. P1 is the probability that the die roll of the die is 1, and P2 is the probability that the top face of the die is 2, and so on. So this P1, P2 up to P6, you can take that as a vector, and that vector is a point in six-dimensional space. Of course, there is a constraint that all the values of P are non-negative and the summation of Pi is 1. So there will be kind of a hyperplane that satisfies that equation, that P1 greater than or equal to 0, P2 greater than or equal to 0, etc. and P1 plus P2, etc. plus P6 is one that gives you a plane, and if you pick a particular point, that will fix your probability distribution. So once P of x is fixed, you can vary the distribution of y given x to vary the joint distribution of x and y. So if you fix P of x, then the mutual information is a convex function of P of y given x. Uh, Conversely, if you fix P of y given x, then the mutual information is a concave function of P of x. The For the proof, see Thomas and Cover textbook. I can do the proof. Okay, let me do the proof. Let me just do the proof. So to prove the first part, that is, if you fix P of y given x, I of x semicolon y is h of y minus h of y given x, which is h of y minus summation P of x h of y given x equals small x, summed over all x. Now P of y is summation of P of x comma y over all x, which is summation of P of x times P of y given x over all x. P of y given x is fixed. Therefore, P of y is a function of P of x. And what type of function is it? It's a linear function. P of y is a linear function of P of x. So It means that h of y, which is a concave function of p of y, which you saw earlier, but p of y itself is a linear function of p of x. So h of y is also a concave function of p of x. So the first term in this sum is the concave function of p of x. Coming to the second term, you have summation of p of x, h of y given x is equal to x, which for each value of x, you take p of x and multiply that with h of y given x is equal to x. So when you take h of y given x is equal to x for a particular value of x, let me do this. H of y given x equals x is nothing but summation over all y p of y given x log 1 over p of y given x is fixed. So this is also fixed since p of y given x is fixed. So given a particular value of x, p of y given x is fixed, and summation of that means log of 1 of p of y given x is also fixed. So that product is also fixed, and summation over all y is also fixed. So it's a fixed quantity. Therefore, summation p of x h of y given x is equal to x over all x, which is h of x given y, is a linear function of p of x. So mutual information is h of y minus h of y given x. Sorry, that was h of y given x. Uh, where h of y is a concave function of p of x and h of y given x is a linear function. So concave function plus a linear function or a concave function minus a linear function is still a concave function. Therefore, for a fixed uh, conditional distribution p of y given x, the mutual information is a concave function of the distribution of x. That proves one part. To prove the second part, fix p of x, and then we consider two different conditional distributions p of y given x and p of y2 p2 of y given x be two different conditional distributions. Corresponding joint distributions are p1 of x comma y, which is equal to p of x times p1 of y given x, and p2 of x comma y is p of x times p2 of y given x. Respective marginals are p of x, which is same for both distributions, and p1 of y for the first distribution, P of x and P2 of y for the second distribution. Now consider a conditional distribution which is a mixture of the two given distributions. So we are trying to show that uh, mutual information is a convex function of the conditional distributions. So we consider a convex combination of the two conditional distributions lambda p1 of y given x plus 1 minus lambda times p2 of y given x, where lambda is a number between 0 and 1. Then the corresponding joint distribution p lambda of x comma y is also a it's also the same convex combination of the two joint distributions. And the distribution of y, marginal distribution of y, is also a convex combination of the two marginal distributions, p1 of y and p2 of y. Now we have to consider for mutual information the relative entropy between the joint distribution and the distribution of the products of the marginals. So let q lambda of x comma y be p of x p lambda of y. From this we have q lambda of x comma y is equal to lambda q1 of x comma y which is lambda times p of x times p1 of y. So q is the product of the marginals in all for all subscripts. So q2 of x comma y means p2 of x times p2 of y, which is nothing but p of x times p2 of y. Now the mutual information I of x semicolon y is by definition the relative entropy between p of x comma y and the product of p of x times p lambda of y. Now we already showed that d of p parallel q is a convex function of p comma q. Therefore, mutual information is a convex function of it's a convex function of p comma q in this case also, but for a fixed p, uh, since p of x is fixed, then p of x comma y is a function of p of y given x, and p of x p of y is also a function of p of y given x. So it's a convex function of the conditional distribution. Alright, that's the proof. Now we'll move on to the data processing inequality. And before we move on to the data processing inequality, we need a few definitions and facts. So definition: random variables x, y, z are said to form a Markov chain in that order denoted by x, y, z if the joint PMF can be written as P of x comma y comma z is equal to P of x times P of y given x into P of z given y. So P of x, y, z, according to basic probability, would be equal to P of x times P of y given x times P of z given x and y. So in a Markov chain, we are saying that P of z given y is equal to P of z given x and y. That is the conditional distribution of z given y is independent of x. So from this, there are a few simple consequences. First one is that x, y, z is a Markov chain if and only if x and z are conditionally independent given y. That is p of x comma z given y is equal to p of x comma y comma z given by p of y, which can be written as p of x comma y into p of z given x comma y by p of y. But since it's a Markov chain, p of z given x comma y is nothing but p of z given y. But p of x comma y by p of y is nothing but p of x given y. So this becomes p of x comma z given y is equal to p of x given y times p of z given y. And that means x and z are conditionally independent given conditioned on y. Second fact is that if xyz is a Markov chain, then zyx is a Markov chain. Hence, the condition is sometimes written as x double arrow y double arrow z. The third consequences is that third consequence is that if z is completely a function of y, that is, it completely depends on y, then given y, z is known. So z is independent of x. It only depends on y. That means x, y, z forms a Markov chain. So if z is a function of y, x, y, z forms a Markov chain for any random variable x. Now we know all these facts about Markov chains. We can use that to prove the next inequality. It is called the data processing inequality, which is one of the most important inequalities in information theory. So this inequality tells you that if you have certain information about, say, there are two random variables x and y, and you are allowed to observe y, which will give you some information about x because there is some mutual information, some non-negative mutual information between x and y. So by processing y or doing some manipulation with y, you can't increase the amount of information that we can get about x. So observing random variable y is the best you can do. Further processing of y will not give you any more information than directly observing y. In symbols, that is, if x, y, z form a Markov chain, then the mutual information between x and y is greater than or equal to the mutual information between x and z. So this is for any Markov chain. Z does not need to be a function of y. But suppose z is a function of y, then that means you have done some manipulation on y. But doing that manipulation didn't give you any more information than what y already gave you. The proof of this is as follows. We use the chain rule and we write mutual information between x and the set yz is equal to the mutual information between x and z plus mutual information between x and y given z. You can also write this as the mutual information between x and y plus the mutual information between x and z given y. Since x and z are mutually independent given y, I of x z given y is 0. And from non-negativity of mutual information, I of x y given z is greater than or equal to 0. So this quantity is equal to 0. This quantity is greater than or equal to 0. Therefore, I of x comma y, which is equal to I of x colon z, x semicolon z plus I of x semicolon y given z. As this is a non-negative quantity, we can remove that and we can write I of x y is greater than or equal to I of xz. With equality, if and only if I of xy given z equals 0, which implies x and y are mutually independent given z. That is, observed giving z gives you all the information that you can get about x. Observing y does not further give you more information once the z is already known. Then I of xy is equal to I of xz. Otherwise, I of xy is always greater than or equal to I of xz, greater than I of x. And this can also be written in the words as x, z, and y form a Markov chain. That's the proof of the data processing inequality. We'll look at two corollaries. One corollary is if z is equal to g of y, that is, z is a function of y, we have I of xy is greater than or equal to I of x g of y. Proof xy g of y is a Markov chain. That means g of y, which is a function of y, which you could say you've done some processing on y or some manipulation of y, it doesn't need any extra information than what y would directly give you. Another corollary, if x, y, z forms a Markov chain, then I of x, y given z is less than or equal to I of xy. So we had seen in a previous lecture, no, sorry, we saw it right in this lecture at the right at the beginning, um, that information can't hurt. That is, conditioning reduces entropy, much of um, x given y is less than or equal to h of x. So this theorem Analogous to that, we have this theorem for mutual information. It is I of xy given z, conditioning I mutual information with z will reduce the mutual information I of xy given z less than or equal to I of xy. But in this case, it only holds if xyz form a Markov chain. That is, z and x are mutually independent given y. First, we'll see proof of that. I of xy z is I of xz plus I of xy given z. It's also equal to I of xy plus I of xz given y. But xyz form a Markov chain. So I of x z given y is 0. Non-negative or mutual information guarantees that this is greater than or equal to 0. Therefore, I of xy, which is equal to I of xy given z plus I of xz, which implies I of xy is greater than or equal to I of xy given z. And we'll take this as a note. I of xy given z greater than I of xy is possible if xyz does not form a Markov chain. We can see an example of this. Suppose x and y are fair, independent, binary, random variables. Say x probability of x equals 0 is equal to probability of x equals 1 is half, probability of y equals 0 equal to probability of y is equal to 1 is equal to half. Joint probability of xy is probability of x times probability of y. That is, the value of x does not depend on y, value of y does not depend on x. Then let z be the random variable x plus y. The mutual information between x and y is 0 because x and y are mutually independent. But z has the probability distribution. So z can take the value 0 if both x and y are 0, can take the value 1 if x is 1 or y is 1, but x is 1, y is 0, or x is 0, y is 1. Can we take the value 2 if um, let's write down the uncertainty in x, h of x given the value of z. H of x given z equals 0. If you know that z equals 0, that is x plus y is 0, then that means x must be 0. So there is no uncertainty in the value of x. H of x given z equals 2. We know that z equals 2. We know that x plus y is 2. That means both x and y must have been 1. So there is no uncertainty in the value of x. So that's also 0. But h of x given z equals 1. So if z equals 1, then either x is equal to 1, y is equal to 0, or x is equal to 0, y is equal to 1. So x can be 0 or 1 with equal probability. And that is, given z equals 1, probability that x is equal to 1 is nothing but the probability that y is equal to 0. And probability that x is equal to 0 is nothing but the probability that y is equal to 1. Um, so this is h of half comma half. Because given z is equal to 1, there are only two possible outcomes for the pair xy. So 0, 1 or 1, 0, and both outcomes are equally likely. So x is equal to 0 with equal probability as x is equal to 1. So the normalized distribution is half half, which gives you half plus half 1 bit. What is the probability that z is equal to 1? That is the probability that x is equal to 0 and y is equal to 1 plus probability that x is equal to 1 and y is equal to 0. Actually, there should be probability that x is equal to 0 times probability of y is equal to 1 given x is equal to 0. But since y is independent of x, it becomes probability of y is equal to 1. So this is nothing but half times half plus half times half. which is half. So now the conditional mutual information I of xy given z is h of x given z minus h of x given y and z. So given y and z, there is no uncertainty in the value of x because x is equal to z minus y. Therefore, this is equal to 0. Therefore, this is equal to h of probability of z equals 0, h of x given z equals 0 plus probability of z equals 1, h of x given z equals 1 plus probability of z equals 2, h of x given z equals 2. But this is 0, this is 0, as we saw here. The only one left is probability of z equals 1, which is half times uncertainty in h, uncertainty in x, given z equals 1, which is 1, which is half bit. As you can see here, I of xy is 0, but I of xy given z is half, which is greater than I of xy. So since here xyz don't form a Markov chain, it is possible that I of xy given z is greater than I of xy. When we talk about uncertainty, the entropy, it is always true that h of x given y is less than or equal to h of x. But in case of mutual information, I of xy conditioned on z can be greater or can be lesser or can be equal to I of xy. So we can only tell what it is in case it's a Markov chain. Otherwise, we can't tell. All right. That is all about the data processing inequality. In the next class, we'll see a bit about sufficient statistics and Fano's inequality, and that will cover all the basics of information theory. After that, we will see asymptotic equipartition property and channel coding and channel capacity. We'll see how much we can cover.